Alright, so in this video, we're going to be talking about asymptotic complexity. And in this video, I'm mainly going to focus on the ideas, and I apologize in advance, my handwriting is not very good. You might see me, write N, and it looks kind of like my H. So I mean, I'm probably not going to write any H's, but if you see me write an H, I'll use it like this, maybe. But, if you see this, it's basically an N. Also, I'm terrible at drawing, so I apologize, about that, and the scale might be a little bit messed up, but hopefully you'll get all the ideas, and that's really what I'm making this video for, and I'm partly making it for myself as well, because I'm a computer science student, and as I keep on learning things, I always have to go back and reteach myself some concepts every once in a while. We're talking about asymptotic complexity here. The general idea is very simple. We'll talk mainly about big O right now. We'll talk about some of the others later, but for now, let's say that we have some function, and real quick, this is a graph. It's a Cartesian plane. Although we don't care about negative values, all we care about are positive values, because really what you can think about this is kind of like some amount of data, and we can call that n. So we can say something like f of n is equal to n, and this is that line that we have right here. So if we go up here to 1, this is going to be our x value. This is the amount of data that we have, so we can, have this at like 1, 2, 3, and it doesn't really matter. You can call this a gigabyte or whatever. The units aren't really important, but what matters is the idea. So if we have, one piece of data and it takes, 1 second to process, then we have 2 pieces of data, and that takes about 2 seconds to process, and then, this will be lined up with, 2 over here. And again, this is not to scale, but, this is a general linear function where f of n is simply equal to n. However, we can also have, something else, like, for example, g of n, and that will be, n squared. And so g of n will look something like this. And obviously, it's an exponential function, so therefore it's going to be growing at a much faster rate. However, it's worth noting that before this point of 1, right here, where k, we're going to call this k, is equal to 1, it is n is equal to 1, but I'm going to call it k for a reason, and I'll talk about that later. But it is, a value of n. But this is really an important point because, after we get to this point, everything after this point of k, for every value of n, where n is greater than k, right? Because where n is greater than 1 in this particular case, k is not always going to be 1, but in this particular example, it is 1. So whenever n is greater than 1, we always have this case where it is true that g of n is greater than f of n, right? And that's essentially what it means to be an upper bound. Because even though, obviously exponential functions grow a lot faster, but it is worth noting that at the beginning, this exponential function is actually below n. Because, f of n, if f of n is, let me get a different color here, f of n is going to be, well, if we say that n is equal to 1/2, f of 1/2 is simply going to be 1/2. However, if we have our g of 1/2 is going to be 1/4, right? Because this is going to be 1/2 squared, so that's just going to be equal to 1/4. And what that means is that at that particular point, f of n is going to be greater than g of n. Right? And that's only at the point 1/2. But for most of the graph, for everything from 1 all the way up to infinity, g of n is always going to be greater than f of n. So that is essentially what the upper bound is. It is an upper bound because for the most part, this g of n is going to be greater than f of n. Because you'll never see this point where, where g of n drops down below f of n. That's not going to happen when g of n is n squared. Now, if you had something like a logarithmic function, that might eventually happen. But, right now, we're only concerned about these two functions. So really what we're focused on is kind of the n behavior, right? Because, if this were kind of like curved upwards where it's going straight up, and this, purple one right here, if this were, kind of, going in that direction, then you can see that this arrow is eventually going to get to the point where it's higher than this arrow right here. And that's essentially what we're looking at. We're considering what is the end behavior of these two different functions. All right, so here is more of a formal definition, right? T of n is considered big O of f of n if and only if T of n is less than or equal to some constant c. This can be any number, but it needs to be multiplied times our function f of n. And that is true for all values where n is greater than k. And again, remember, k in this particular example was equal to 1, but k doesn't have to be 1. K could be any, different, depending on the two functions you're comparing, it's going to be a different value. One other thing I don't have here is that both c and k need to be greater than 0. But I'm going to go ahead and get rid of that detail, because at the end of the day, it's kind of assumed we're only talking about kind of positive numbers here, because you don't have negative data, you don't have negative time. So real quick, let's ask ourselves, is n going to be big O of n? And let me add a little question mark there. We're just asking ourselves, is this the case? Is n O of n? So here we can say that T of n is going to be our n, right? T of n is going to be n, and we'll just go ahead and draw that out. It's a straight line. Again, looking at this definition, T of n is O of f of n if and only if T of n is less than or equal to some constant c times f of n. So in this particular case, our T of n is this left side right here, n, and our O f of n is going to be this n right here. So f of n is going to be n. And it's a little confusing because they're both n, but here's where we're going to be asking ourselves, T of n is less than or equal to c times f of n. So we have a c. So T of n, again, remember, is going to be this purple n. And that is going to be less than or equal to, and then we have some constant c times f of n, c times, and then our blue n right here. Because remember, the blue n corresponds to f of n. So what we're doing is we're going to be multiplying this by any number. We can pick any number. I'm going to go ahead and say that c is equal to 2, right? So in this example, we're going to say that c times f of n is going to be equal to 2 times n. And again, we're just saying that c is equal to 2, and f of n is still equal to n. And this is the same f of n right here. All right, so let me use a graphing calculator because it's a lot better than my drawing. We just have a graph here. This is, we have to use x, unfortunately, because if I use n, then the graph doesn't understand what's going on. But x, n, same thing, doesn't make a difference. But yeah, so we have, if our x is going to be 2, then we have an output of 2. If our x is 4, we have an output of 4. So if we have our c value and our c value is 2, then that means that our graph is going to look like 2x. And that means it's going to look like this. They both start at the same origin. They're not exactly parallel, but you can see that 2x is always, always, always going to be greater than x. And that is the definition of, being upper bounded. This is an upper bound because this blue line is always greater than this purple line underneath it. Now here is another question I want you to consider, and you can pause the video and try to figure it out, but is n going to be a lower bound for n? And assuming you paused the video or chose not to, the answer is yes. If our c value is equal to something like 1/2, you can see that this red line, which represents our 1/2 x, is going to always, always, always be below our function f of n is equal to n. Or in this case, f of x is equal to x. So it doesn't matter what the value of x is, the function f of half x is going to be below f of x. So therefore, we can say that this red line is a lower bound of x. And it's really the same idea, but, the opposite. And likewise, I want you to also consider if c is equal to 1, I'm going to draw that in a yellow line, but hopefully you can, guess. If c is equal to 1, it is just directly on top of this purple line. And I might not draw it well, but it is literally the exact same line. So when we have an upper bound like this, where c is equal to 2, we call that big O. And when we have a lower bound, like where c is equal to 1/2, then we have big omega. But in this case, we have big O and we have big omega, meaning we have big theta, right? And also the sign for omega is this ohm here. Theta is just going to be, the theta sign, and then here is just big O. It's just a big O. The c value, all that really does is modulate the line where we get bigger and bigger values of c, and you can see that, the line is eventually getting to the point where it just, goes straight up. And likewise, if we continue to decrease the value of c, you can see that we are getting closer and closer to the x-axis. And if you have a different function, like for example, a parabola, you can see that, a larger c value will essentially shrink the parabola. So if we have a very, very large c value, like here we have our c value would be 100, you can see that this blue parabola is, shrunken a lot. And if we change that to 1,000, eventually we're going to get to the point where, again, we're directly on the y-axis. And likewise, if we were to create smaller and smaller values of c, where we're approaching 0, you can see that the parabola is getting stretched out bigger and bigger. But again, remember, we really only care about what's going on in this top right quadrant here. We don't care so much about the negative behavior. All that really matters is that we can find any one c value. It doesn't matter if it's 1, 2, 3, 4, 5. We just need to prove that there is a c value where it is true that for all values of n, where n is greater than some value k. And again, remember, k could be something like 1. So wherever n is greater than 1, and I think it's a little more confusing because, you have a lot of variables going on. But all we're saying is that whenever n is, past the point of 1 or 2 or 3, if our k value is, if k is equal to 3, when the k value is 3, all we're really saying is we don't really care what's going on this side of the graph. All that matters is what's going on this side of the graph right here. And on this side of the graph, is it true that this line is always going to be greater than this line right here? And there are going to be examples of functions where it doesn't matter what the value of k is. For example, in this graph, it doesn't matter what k is because, if we have, this function where we said, again, this is going to be 2, right? This is 2 times f of n. It doesn't matter if n is equal to 1 or 2 or 3. It can even be 1/2 or 1/4 or 1/8. In this particular example, it is true that 2n is always going to be greater than just n, regardless of what the value of n is. But not every function comparison behaves that exact same way. Again, remembering the previous example where we have some kind of exponential function, there is going to be some point where this exponential function is below the original n value. However, once we get to this particular value right here, which is our k, it doesn't matter what the number is, but once we get to this point, every single value of n is going to have a greater output. And so therefore, we don't really care what goes on the left side. But there are, certain functions where it doesn't matter at all what the value of k is. So hopefully all of that makes sense. What we're focused on is this definition here. Is there any one value of c where it is true that c times f of n is less than or equal to t of n? And that needs to apply for all values of n where they are greater than k. All right, so far we've talked about big O, and this is going to be the upper bound. And then we have big omega, and this is kind of that horseshoe looking symbol, and this is going to be the lower bound. And then we have big theta, and this is going to be when we have both big O and big omega. So this is going to be, the tight bound. But then we also have little o and we have little omega. So these are not as common, but these are considered to be kind of a loose upper bound and then a loose lower bound. So the idea is pretty much the same. And we can call this f of n, and that'll be n. And then we have some other function, and that will be going off this way. And that'll be g of n. And that can be n squared or n cubed, it doesn't matter. So let's focus on little o because, if you understand the upper bound, it's really easy to understand the lower bound. And if you understand the loose upper bound, it's really easy to understand the loose upper bound because really it's just the opposite thing. So let's pull up a definition. A function f of n is little o of another function g of n, and this is just an example, exactly when, for all positive real numbers c, there is a positive integer, and this is n naught. I wrote down k. N naught and k are interchangeable. It doesn't really matter which one. Such that for all values of n greater than that k value, f of n is less than or equal to c times g of n. So it's a very similar definition. The main difference right here is that for all positive real numbers C. That is really the main difference between little o and big O. And what we're saying again, remember, before we had a line, and then we had another line, and then we had another line. They were all different. One might be 2n, one might be n, and one might be half n. So in this case, this would not be little o. However, you can see that it is big O because there exists some number C where, this is greater than that. However, it would not be little o because the requirement for a function to be little o, to be a loose upper bound, is that for all values of C. We can see here that this value of C always stays below this line, so therefore it would not qualify as a loose upper bound. But coming back to our example here, right, where we have f of n is equal to n and g of n is equal to n squared. So now let's ask ourselves, is f of n going to be O of g of n here? Is f of n, is it little o of, and then let me change my color here. So we have g of n. So again, we're asking, is n going to be little o of n squared? And I'm not going to give you a formal proof, but the answer simply is yes. And that's because it doesn't really matter what your C value is, right? What we're really doing is saying, is n always going to be less than or equal to every value of C times n squared? Meaning, is it true that no matter what C is equal to, this yellow line here, is it true that this yellow line is always going to eventually, at some point, when we approach infinity, is it eventually going to, go past this line and exceed it at some k value right here, or you can call n naught, but that, it doesn't really matter what you call the variable. And hopefully, if you know anything about exponential functions, you realize that, the yellow line is always going to grow at a much, much, much faster rate than this blue line right here, the linear line. So it doesn't matter if C is, 1 over 4, or if C is 1 over 8, or C is 1 over, 100, or 1,000. It doesn't really matter what C is. At the end of the day, there's eventually going to be some point going closer to infinity where, we end up with this fact that the yellow line is going to exceed the blue line, and that for every value where n is greater than k, where k is whatever this point is, it doesn't have to be 1, it doesn't have to be 2, it could be 10,000, it could be 1,000,000. All that matters is that there's going to be some point where this line is always, always, always going to be above this line down here. And again, this is not a proof. I'm going to be talking about how to do the mathematical proofs. I just want to give you the intuition, the logic that hopefully you realize that no matter what value of C there is, this function is always going to grow faster. So therefore, it is a loose upper bound, meaning therefore n is little o of n squared. And one other thing to point out is it is a little bit unintuitive because little o is a loose upper bound, whereas big O is an upper bound. Big O is really just asking, does it exist the case where, there is some value C where this line is constantly always staying above that line. However, the little o is asking, is it always the case, no matter what value of C? It doesn't matter what C is it always true that we have this deviation, and in a sense, it is a greater deviation than big O. So that's a little counterintuitive to me, to think that, okay, this is little o, but the deviation is bigger, and big O has a smaller deviation. However, that is the naming convention that people chose, and it doesn't really, mean anything other than somebody decided that that was the better, terminology. So hopefully all of that made sense, and it won't make things more confusing, especially as we move on, because I'm going to go on to some mathematic proofs for big O, big omega, big theta, and little omega, and they're not that difficult. And then after that, we're going to talk about the master theorem. But at the end of it all, it's not really that complicated. The math is not that complicated. It's actually pretty intuitive if you kind of know what's going on. But I had a hard time trying to find, very thorough discussions online, talking about this. So I decided to make these videos. If you thought that this video was helpful in any way, please, leave a like and subscribe, and I'll be uploading more as I go. And that's pretty much all I've got for this video. So thank you for tuning in, and hopefully, we'll see you in the next video.